We've seen in previous videos that if you take an intrinsic semiconductor and add a group 13 element like say boron, which has only 3 valence electrons, then it accepts electrons, it acts like an acceptor impurity, and as a result ends up giving us a lot of holes. And so the boron itself becomes negatively charged, but it's immobile, it can't move, it's a bulky thing stuck in the crystal, but the holes are now the majority charge carriers. And as a result, we can imagine that we now have a bed of negatively charged semiconductor, on top of which we have this gas of holes. Nice way to visualize this, which acts like a blanket. And as a result, the whole thing is still neutral, since the majority is positive type holes. We call them as p-type semiconductor. And similarly, if you dope it with, or if you add a group 15 element like phosphorus, which has 5 electrons, 1 extra electron, it ends up donating that. As a result, ends up getting a positive charge, but still these phosphorus ions cannot move, they're immobile, they're pretty much stuck. And again, we can assume that it's a bed with a positive charge, a stuck positive charge, and you have a gas of electrons on top of that which are randomly moving around, and as a result, again, the whole thing is neutral. And since we have the majority as the negative charges, we call this as n-type semiconductor. And we've talked a lot about this in previous videos, so if you need more clarity on this, it'll be a great idea to go back and watch those videos first and then come back over here. But in this video, we're going to do the most tempting thing ever. We're going to take a p-type and n-type and join them together like I've seen over here and ask the question, what's going to happen? So let's do that. So if you take these two separate crystals and sort of glue them together, then nothing will happen. Because if you glue them, there will be still a lot of microscopic gaps in between, and as a result, it will act like two different containers having gases, and nothing can happen. If you really want something to happen, you have to build a single crystal, one single crystal, with p-type on one side and n-type on the other. And building that in reality could be a little bit complicated, but let's just assume that we end up doing that. And let's just stop this animation for a while. It's giving me a headache. There we have it, a single crystal with a lot of holes on one side and a lot of electrons on the other. Just pause this video and think what will happen. Now we might think that electrons and holes attract each other because one is negative, another one is positive, but this is wrong. This is a huge misconception. Don't think of it this way. Holes can't attract electrons because in reality, holes are not really particles. Remember, they are absence of electrons, they are vacant sites in covalent bonds. They cannot attract electrons, so don't think of it that way. A better way to think of them is as gases. Imagine that you have one kind of gas on one side of a container and another kind of gas on the other side of a container, and the partition between them is removed. What will happen? Well, we know what happens to gases. They end up mixing with each other, and we call that as diffusion. It's a random process in which particles end up moving from a high concentration region to a low concentration region. Since we have a lot of holes over here, these holes will end up diffusing into the n-type, and similarly, these electrons over here will end up diffusing into the p-type. But notice that diffusion can only happen over here. You wouldn't expect diffusion to happen over here. You wouldn't expect these holes to start moving like this because remember, there might be a lot of holes, but there is no difference in the concentration. And similarly, no diffusion over here. So diffusion is only happening very close to the junction. And notice, because of the diffusion, electron holes are coming very close to each other. And when they come very close to each other, we know that they end up destroying each other, recombination. And so right at the junction, those charge carriers are completely destroyed. What happens next? Well, next, we might expect the diffusion to kick in over here and here. We might expect these holes now to diffuse and these electrons to diffuse, and they might recombine. And eventually, as time progresses, we might expect all the holes, slowly and steadily, all the holes and electrons would have diffused into each other, mixed with each other, just like how gases would do, and they would have recombined and destroyed each other, removed all the excess holes and electrons. That would be extremely bad because we worked so hard to get to this point, right? Well, fortunately, that doesn't happen because there's one key difference between gas molecules and holes and electrons. We are dealing over here with charged particles, and as a result, all the holes and electrons won't mix with each other. This mixing will stop immediately. Can you think why that would happen? This is important. I want you to pause the video and think, but just look around and just see. Can you come up with a reason as to why all the holes and electrons won't mix together? Well, the secret lies over here. Notice due to the earlier destruction of charges, they have exposed the negative and the positive ions. And now as a result, when more holes try to diffuse over here, notice that these positive ions start repelling these holes. And as a result, when they try to go there, due to the repulsion, they can't make it and they have to turn back. They end up turning back. And similarly, when the electrons try to diffuse, I mean, forget about this hole, that's a minority, don't worry about that as of now. When the electrons try to diffuse over here, notice these boron negative ions, they start repelling the negative electrons. Again, they go try to diffuse up, nope, they can't do that. And so notice, because they have exposed these charge carrier, these immobile ions, the impurity ions, that acts like a barrier for diffusion. But diffusion may not give up. There might be some molecules, some holes and some electrons which are energetic enough. Maybe these holes might be energetic enough that even after repulsion, they might still diffuse. And similarly, there might be some electrons over here on the other side which are energetic enough, and even after the repulsion, they might still diffuse. But notice, they might go over here and they might get, recombine somewhere. Similarly, these might end up recombining somewhere because there's so many places to recombine. But notice that the more they diffuse, more ions they expose, and they make it even harder for diffusion because the repulsion starts increasing. So I think we can see where this is going. As the diffusion continues, we see that more and more charges will get exposed, ions will get exposed, and as a result, diffusion might slow down and might eventually stop, right? Well, not quite. You see, it's right that the diffusion keeps slowing down because the barrier starts increasing, the repulsion starts increasing, but there are always electrons and holes energetic enough to overcome that barrier and still keep diffusing. We always have them. So what will happen eventually? Well, we've been ignoring the minority charge carriers far too long. Remember, in the p side, we have these electrons, over here and here, some few electrons, and on the n side we also have some holes. Well, we didn't talk about them so far, but what happens next, they play a key role in it. So let's focus on one electron. Let's say we take one minority charge carrier over here. Notice that nobody cares about that. Everybody's about diffusion. So it's just minding its own business. It's just doing, it's wandering around. It's pretty lonely. And suppose it enters into this region over here near the junction. Notice, because of this positive charge, it starts attracting the electron, and zoop, it goes into the n-type. It gets sucked into the n-type. And similarly, if you have, like, say, a minority charge carrier, let's say a hole, again, nobody cares about this. It can't diffuse. It's all about diffusion. Everybody's just focused on diffusion. It's lonely. The poor folk is just going over here, and finally, he enters over here, and now, notice the negative charge will attract the hole, and zoop, the hole will get sucked in. Can you see that there's a second kind of motion that's happening completely in the opposite direction? I mean, think about it. For diffusion, the holes are moving from p to n, and these charges are acting like a barrier. But notice, for minority charge carriers, like a hole in this region over here, there was a hole over here, let's see, there were holes over here. For the minority charge carrier, the motion is in the opposite direction, and this charge is actually aiding the motion. It's benefiting that motion. Can you see that? So there's a second kind of motion that's coming that's in the opposite direction of the diffusion. And so as time passes by, diffusion starts decreasing, but this second kind of motion starts increasing. And since the two are in the opposite direction, eventually we will reach a point for every hole that diffuses into n-type, one hole will get sucked back due to these charges. And similarly, for every electron, for every energetic electron that still manages to diffuse to the other side, one electron will get sucked back. And when this happens, notice that on an average, the total number over here and the total number over here on an average remain the same. And that is when we would have reached our equilibrium. So that's the story of p-n junction. Very interesting, very subtle concepts, but yeah, it was very intense. So let's quickly summarize. When the p-n junction just gets formed, majority charge carriers start diffusing. The holes start diffusing into the n, the electrons start diffusing into the p, and as a result, they start recombining and destroying each other, and they expose the charge on the impurity ions. This starts acting like a barrier which slows down diffusion, but diffusion still continues.
But now the minority charge carriers start getting sucked in due to these charges in the opposite direction. Eventually, equilibrium is reached when for every hole that diffuses, one hole gets sucked back, and for every electron that diffuses, one electron gets sucked back. And now equilibrium has reached. And this device is super useful because this will act like a one-way conductor.